Heisenberg's uncertainty principle. Heisenberg's uncertainty principle of quantum mechanics states that both the position and the momentum cannot be simultaneously be known with infinite precision at the same time. Let's take a look at mathematically how this expression is being derived. We start off by using the wave particle duality expression. P lambda is equal to h. And from there, we can assume that the wavelength of the light used to locate the object's position is lambda. Hence, the change in displacement is approximated as the wavelength. When a photon strikes the object, the change in momentum can therefore be estimated by this expression. Do note that in this formula that we're using in Heisenberg's uncertainty principle, both change in P and change in X are both vectors. Therefore, they must actually be in the same direction. So let's take a look at some example. A simple example is that if we have a ball that's moving this way with a momentum P, then what happens is that if you're trying to locate the ball, we need light to shine on it. So when light shines on it, photons fall on it. And when photon falls on it, what this Heisenberg principle is saying that the momentum will now changes. Because the photon also has a certain momentum, it will actually affect the momentum of this ball. And the change in the momentum, and based on the change in momentum, we will now be able to locate the position of the ball, which is the change in X, based on the Heisenberg uncertainty principle, which means your change in X is actually H over change in P. So in summary, if the change in P of the ball is very big, then your change in X will be very small, and vice versa. So in another example, what we have is actually an electron initially at rest, and it's moving with a momentum P. And to determine the position of the electron, light will be shined on it, and consequently, there will be photon colliding with the electron. In the process, the electron will have a change in momentum. Therefore, the position to locate the electron will be change in X, and change in X multiplied by the change in P must be equal to Planck constant. And it's important to note in this example that the direction of your change in momentum is in the same direction as the change in X. Okay, let's take a look at now how we can use the Heisenberg's uncertainty principle to determine the atomic size of the atom and the size of its nucleus. The information given is that the energy of an electron found in the atom is 9.4 MeV. So 9.4 MeV is actually the kinetic energy of the electron. And we can make the Ke be equal to half P squared M. The purpose is to actually determine the momentum. So once we calculated the momentum, we can assume that the momentum change, the maximum momentum change for an electron is this. And if your change in X is the maximum possible value, then your change in M, in this case, is the minimum possible value. So once you calculate the change in X, it means that you can locate the electron with an uncertainty of change in X, which in this case is 4 times 10 to the power minus 13 meter. That is an estimate of the size of the atom. In the case of the nucleus, we'll be doing exactly the same calculations. In the case of the nucleus, the energy of the electron found in the nucleus is 3.77 giga electron volt, which is actually significantly higher than your 9.4 MeV. So you can see that the momentum of the electron is now of a higher value. We can now assume that the maximum change of the momentum is this value. So therefore, we can locate the position of the electron with a precision of change in X, and change in X is 2 times 10 to the power minus 14 meter. So that is actually the estimated size of the nucleus.